So Jan, thank you so much for being here.
Thanks for having me.
Really appreciate it. So let me start by asking you, so we can get going, your start in academics. What shaped your early life in computer science? What was your early passion to get started? Your early passion to get started.
Early passion before
Before Berkeley, the labs and everything.
I grew in Romania, Eastern European country. It was under communism back then. And like many people there, I actually obviously was not obvious, but I was I was pretty good at math, physics, and actually the one thing I can say is that probably more unusual it was before, after the elementary schools, which in Romania is the first 4 years, not like here 5 years. The following 4 years, I also followed in parallel kind of an art school. So, doing this kind of, it was 3 days per week, doing sculpture, drawing, and whatever, painting. And I remember that when going to high school, you have to pick your career. At least for a moment, I was thinking to go on the other side of the brain, so that's one. And then after the high school, during the high school, there are all these kind of competition and so forth. So I was participating, math and physics. So one thing I was thinking very seriously then, whether to go to computer science, what was then, or physics, because physics actually in Romania back then was very well funded. And because there are some direct connections with Ceausescu, which was a dictator back then. But I picked computer science, and then I did my college in Romania, and then I come to US to do my PhD.
So you were at CMU, you came on, every college wanted you, you went on to Berkeley.
Yeah.
And beyond all the teaching and work you've done, and you've become obviously a powerhouse for starting companies, but I think one of the things you've done that's phenomenal is created all these great research labs. The AMP lab, the RISE lab, Sky lab.
Yeah.
Can you tell us about how you formed these research labs and how they've progressed to be the powerhouses they are?
Yeah. The phrase you are on the shoulder of the giant. So labs, Berkeley, has different kind of labs, like many schools, but the labs I've been involved with are quite different, and they were started long time ago by Dave Patterson, Turing Award winner, Randy Katz, and others, long before I came to Berkeley. And this style is like 5 years labs. So if you can treat a lab like a project, a bigger project. So what happens is that a group of faculties come together before the lab starts and see, again, what are the next topics they are interested in. And they put that together, and then around that idea, you have a few faculties with their students. And then for the next 5 years, they are going to work on that particular problem. So previous labs long time ago are the labs which produced risk-reduced instruction set computing, at least on the Berkeley side, RAID, redundant array of inexpensive disk, or now network of workstations, which was one of the first efforts to build our parallel compute infrastructure on top of commodity hardware, right? Commodity servers, right? So in the era of hypercomputing, right, when everything was a supercomputer. So that's kind of the thing. So it continues there since I came, and by Berkeley. So we follow this, and RISE Lab, AMP Lab, RISE Lab, Sky Lab are instantiation of follow the same pattern.
Interesting. And you told me before when we were chatting that these used to start with university funding,
Yeah.
Government funding, and then as you were able to give them star power, you could start to transform them and attract philanthropic
Totally.
support.
So yeah, I arrived at Berkeley in 2001, and spring, and it was the first lab then, and I think when the second lab started, it was Rad Lab probably in 2004 or so. So what happened before the labs, one of the main sources of the funding were DARPA, and of course, National Science Foundation. But after 2000s, at least things started to change, especially with DARPA. And by the way, DARPA was funding the research, MIT, Carnegie Mellon, is like for years, right? For the most major project, the money coming from DARPA. And so now that with that funding actually drying out, actually there was still funding, but they are changing the rules. So you have to work very, and collaborate very strongly with one of these kind of companies and defense industry. So it was very hard, right? Very high overhead. So then I remember Dave Patterson and so forth, like trying to figure out another source of finance, funding, and we started to look much more aggressively at the companies in the valley. Google was raising at that time and a few others. So, and that's why we started most of the money after that, funding these labs, they came from industry. And all the money that came to industry this money comes as gifts. So there are no string attached. There are advantages to have the gifts, not beyond the fact that you have ultimate freedom. It's lower overhead and things like that. But the other immediate impact was that we are starting to these labs are always working together with the industry, but now, because the main source of funding was coming from industry, it was even closer connected to the industry. So I think with that was really beneficial for us. That's why I gave two examples where it's very beneficial. 2006, this was Rad Lab. It was a lab around building reliable distributed computing.
Right.
Okay?
Right.
And as Ad Labs at that time, we are talking about the lab to build our own clusters computers. Actually, we talked with Olois San. San was also at that time a founding member of the lab. And we get, I don't know how many people remember, they have these containers, ship containers, like a cluster in a ship container. So we had that one of those outside Soda Hall, which is a computer science building. So very cool. But this 2006, and again, we have a part of this lab, we have 2 retreats every year. And where everyone, the people from industry comes and students showing the, latest progress we made on the research and listen for feedback. So we had this meeting, and we are talking about planning, for the cluster. And James Hamilton, who was then at AWS, he said, "Hey, AWS will have this kind of things like it's going to S3 and EC2, so." Why do you need to build your cluster, right? Why don't you try that? And by the way, we are also giving you credit. Right? so it's like, it was pretty compelling.
Yeah.
Right? And because you are struggling, we do have heat in our, basement, or you put our clusters and things like that. So that's why how we started very early on with the cloud computing, right? This is one thing. The second thing was, this was earlier on also later on, a few years later, actually very few years later, we were working another kind of funding sponsors was Yahoo. And what Yahoo was doing then, well, they are building Hadoop, Eric 14 and others.
Right.
And we are collaborating very closely with them. So that's why, and actually we started to work on Hadoop, we try to improve here and there. And that's why how eventually Spark came to be, right? Yep. So I think that if I look back, there are some of these kind of opportunities we had which happened, by the way, things were, both environment, of course, Silicon Valley, but also the way these labs have been organized. And again, sometimes, you lose, it turns out that losing the funding from DARPA was good in the long term.
Right. So,
probably, right?
So no one has built labs as well as you have, so those secrets are really interesting now for people to understand. But one of the things that also that I consider you the absolute master of is figuring out how to create great open source projects, communities, and then phenomenal companies out of that. So talk about open source and how that's been the common thread.
That's a great question. First of all, obviously, we like to say at Berkeley, was cradle of the open source long time before. Unix BSD, Berkeley Standard Distribution, Postgres and database, relational database. So many of these things were developed long before I was at Berkeley. And so there was a tradition. But I think that what really get us going, we just, the environment, and it was kind of more in the air, right? You remember that actually what happened, the Hadoop, the emergence of Hadoop led to an explosion of open source software, at least in that space. Hive, Pygmalion, and there are a lot of variants of things, around about all these kind of distributed frameworks. So I think it's one of the things we are in the right place at the right time. And then another thing we have in the lab, because this is what what happens with Spark. We had an interdisciplinary lab. People from AMP, it's algorithm machine people, so this is what the AMP stands for. So we had people from, of course, from system, networking, databases, but we also have people from machine learning. Right? So in some sense, Ray, and I can say more about that, was developed to solve some of the problems of our colleagues in the lab. But going back to the open source, it's again also something about the labs, how they are formed. Because again, you get the funding from the industry. So the easiest way actually to manage it is basically saying, hey, all the artifacts you are building are open source. And by the way, we are not going to file for patents either. It's for public, right source. Because anything else is complicated. Because you have 5 sponsors. Sometimes the companies which are competing among themselves. How you are going to assign the IP? Who owns the IP? So it's very complicated. So in some sense, again, it's like because of the configuration of the lab and where the funding was coming from, that was also one of the easiest thing we could do. And of course, you like to to do the open source because everything is about impact, and having impact, it's very rewarding. So that's kind of what we started.
Fantastic. And then you brought up Spark, which truly is one of the great products of the ages, right? That came out of the open source community that you built. And then Spark led to the start of Databricks. Can you talk about those early years?
Yeah. So Ray, first of all, and again, it's like it's a funny story because I don't know how many people remember, but it was, I think, 2008, 2009, right. Netflix came out with a challenge. And the challenge was they give a set of data and basically say who is going to provide the best ranking, the recommendations, right? Actually, probably many of people remember because they eventually leaked some information with, it wasn't as anonymized as they thought it is. So it was $1 million prize, right? And many kind of research
$1 million prize.
Yeah. So saying it's a prize, who is going to come with the best rating, okay. And many groups in the country and so forth competing with it, right? They are accepting submission and so forth. So you have a team, you have people of machine learning in the lab, and basically they need to compete, right? And they are doing this. This is classic machine learning. It's collaborative filtering and things like that. So it's like, like long time ago in terms of for AI. And we told them then, oh, use Hadoop because you are working on Hadoop. We are, in the community and so forth. So they work on Hadoop, but the next day or so, oh, but it's because they wanted something to scale, right? That's why we told them to use Hadoop. But Hadoop said, but it's so slow.
Yeah.
And it was slow because Hadoop, all these machine learning algorithms are iterative, right, when they train them, right? You train them, the loss rate going down, and each iteration, it's a MapReduce job. A MapReduce job reads data from the disk and writes the data on the disk, and also in between map and reduce to ensure resilience. So that's kind of the problem, and and it was slow. And then Matei, who I was working with Matei then. He said, okay, let me put together something he used together. It was a few hundred lines of code to solve the problem. And solving the problem was to put the data in memory and iterate on the data in memory on different machines. That was kind of Spark. And it was written in Scala because it was an interesting language, but also allow you to do it something quick, right? So that's kind of, how it started, right? So trying to solve that problem which Hadoop didn't solve. And I think that this is one pattern which actually repeated and in my experience led to, to some of the more impactful work. Mm-hmm. So when we try to, it's like when we started to work with a new open source project, we started because the existing systems were not, we tried initially to solve the problem using existing system, but it was, there are some significant gaps, right, architectural gaps. So that's why this is the same with Ray and with, I think, with VLLM. And it was another thing we were lucky when we did Spark, because we have another, actually the first project, it is Mesos. Many people may not remember, but Mesos was very popular as a cluster manager, allowing you run multiple jobs on the same cluster, share the cluster. It was before Kubernetes, right? So that's lost to Kubernetes eventually. But the reason was good because then we have Spark, now we have Mesos, so we can just run on top of Mesos. So we didn't need to build the entire stack for Mesos to, to do all these resource allocations and coordination and starting the cluster, all of this, shutting down the cluster, all of these things. So I think that's kind of, if you look at the first paper on Mesos, actually Spark, it's an example of a framework running on top of Mesos, among others, like Hadoop and MPI, so forth.
Wow. So so Spark basically eclipsed Hadoop.
Mesos was before, and
Mesos before, then
Spark was right after that. They started almost as
and then Spark, and then Databricks started, and then
yes, and then Databricks. I can tell you about Databricks.
Go ahead.
So this story I have, and I saw it's true. So, we are at, Spark is starting to become more popular, and with all of these things, again, it's like, even if you think about altruistically from the point of view of impact, companies ask us, well, what happens when the students graduate, or Matei graduates and so forth? What happens with the project, right? So that was one of the questions. And when we were starting. And actually, at that time, if you remember, there were these two Hadoop companies, Cloudera and Hortonworks, and we knew them quite well. Yeah. People, again, they were found, they are sponsoring our lab. And actually, we went to one company, and we asked them whether they don't want to take over on Spark, so to support it, right, to be successful. And at that time, they were not that keen because they also have some internal projects, which was the next version of the MapReduce. Right. So that's why we decided. It turns out that the timing worked well. I could take a leave, right, sabbatical. Matei was graduating, and there were a few people who are kind of very, Ali was flexible because
there were like six of you. There were like six founders out of Berkeley.
Yeah, it's like, Ali came to our lab in 2009, so 4 years before Databricks. So we have a group of people who are kind of naturally, graduating at that, so or could take a leave. So I said, okay, let's start a company.
Wow.
And that's kind of the story of, but initially we really started as a company because in some sense we want to make sure that, to give Spark a chance of success in some sense. Because again, companies say, we like it and so forth, but they are not willing to commit strategically because who is behind the open source? And by the way, at that time, remember, it was early days also, because who was, like for Linux, you have Red Hat, you have, right, things like that, right? Then you have, for MySQL, you have a company behind it. For Hadoop, you have not only one, two companies behind it, right?
Right.
So obviously, it's like, yeah.
It makes sense. And then, of course, you took Spark, you gave it to the Apache Foundation, and that pretty much solidified at that point. And so then you came back, you were at Berkeley, and then you did it again. You created, Ray was coming out of open source.
Yeah, it's the same thing happens with Ray. I mean, with Ray, I have Robert and Philip took my class. Right. By the way, also Mezzo started in a research class. It's also a tradition at Berkeley and probably other top school. Many of these projects are class projects in graduate classes. And they are actually machine learning people, both of them. So it's coming in and they, class project, it was more of system class. And their project was train deep learning, distributed training, deep learning. This was 2015 or something like that. And okay, what you are going to use? I asked him, hey, you have to use Spark for it.
Right.
So they are students, they listen, and they did train on Spark. Actually, they create, because they have to support the GPUs, and they create kind of a small framework on top. It was called SparkNet. You can look for the paper. So they build that, and then they say, okay, but it's very hard to do it because Spark is Java, JVM, right. So it doesn't support well the GPUs. You need to go GNI to go outside and to schedule and to manage GPUs. And then at that time, it also more things like reinforcement learning and things like that, which are far more complicated patterns. Spark, it's the best for it's parallel data processing. It's more like BSP, bulk synchronous processing model. And while something like reinforcement learning, you need a lot of more flexibility in terms of the computation model. So that's why I say, okay, then we started to build Ray. So that's that's why Ray is obviously not in Java, it's backend is C++, and it's Python, because everyone back then started to use Python, because TensorFlow was there, the most popular, library, and was Python, and of course you have all the other things which are in Python for scikit-learn, also for classic machine learning.
So Ray created an enormous performance improvement for Python development. I mean, I've seen numbers where it's like 50% less resources, 100% of the utilization of what you're doing, but the number of iterations you can do compared to before. So I was at a talk by Bridgewater. They were using Ray with, one of our companies is Domino Data Lab. They were using Ray in conjunction with Domino Data Lab. And because of Ray, they were getting about 4 to 5 times more iterations, faster iteration speed. But I've heard companies like Canva get 12 times. So it's been pretty amazing in terms of a performance boost.
Yeah, so I think Ray is far more flexible in terms about what you can do with it, which it's two-sided, it's always when you have more flexibility, it's an advantage because you can match better whatever your workload to, the infrastructure you are using to run your workload on, right? So you can be more efficient, of course, but then it's also lower level, right? For instance, with Spark, everything looks like a sequential program. With Ray, you need to be aware of parallelism, and this is the lower level. But the second thing, which I think was the second decision, not the second, another decision when we started Ray was to support heterogeneous hardware.
Yes, right.
And actually, today, some of the biggest games you can mix and match, like you do, for instance, things like batch inference, right? Batch inference, you can do a lot of pre-processing on the CPUs, and you do the inference on the GPUs. You can even do, right now, you can even, when you look at the GPUs, there are different types of GPUs with different price points. So you can do like encoding, decoding for lower, cheaper GPUs, like T4s and you can use higher end GPUs for doing inference if you have Llama or whatever, right? So and that's kind of where you gain quite a bit. It's some flexibility of compute because you can do almost whatever you want. You need to know what you do, obviously. And it's in supporting heterogeneous resources.
So now, so AmpLab produced Spark, RiseLab produces Ray. Now you have Skylab. So can you tell people what Sky computing is?
Yeah. So the Sky compute was, born from, and it will take time, born from our needs. So it used to be, I mentioned you about AWS, for a lot of years, we had all credits from AWS almost unlimited. Then things change, and a few years back, I don't know, we started to have less credit, fewer credits. And we started to get, of course, our credits from other clouds, Google, Azure, and so forth. So now you have for a while, actually when we are getting these credits before, the Amazon credits really went down to be painful. So people who have these credits, people who are not using these credits from Azure and GCP, they're using from AWS because all their scripts, everything, and the internal know-how is about how to use AWS. So they are not using anything of those, of the other labs. So Sky was trying, now we also have the problem because now the AWS credits really will drop to the level to be painful, so it needs to use the other ones. So you want to have one way to make it easier for people to run their workloads on different clouds, right? That was one. Now, now the next thing is that you run the workloads on different clouds, but on different clouds you also are going to have different hardware, right? Different accelerators,
right? Or
even with CPUs, right? You have ARM instances like AWS had that very early on, Gravitron. So now you have to support, right? So that's why, and then you build this kind of like inference, like VLLM. Is one of the main things is trying to support different accelerators, right? Because if you cannot support different accelerators, you are not effective. For instance, if I run in Google, probably I want TPUs because I can get credits for TPUs. I'm not going to get credits for NVIDIA's in GPU cloud, right? So it's it's just basically trying to make it easier to run on multiple clouds using different hardware, at least for some workloads, like AI, which are simpler, right? You don't try to boil the ocean because the problem is super complicated, but at least you can hopefully try to solve the problems for some relevant problems.
That's great.
Yes,
fantastic. And knowing your history, I'm sure there'll be a company that's going to come out of Skylab too, right? Anyway, well, I think they're going to give us the hook in a couple minutes, so I'm curious to ask you maybe a last question of what do you think is next? What makes you optimistic for our future?
Well, I am optimistic. I'm optimistic about AI and everything, so I am on that side. I think that if you look about, there are a few trends, and always try to look at the trends. I'm going to mention two. There are many interesting problems. I'm sure you guys everyone looks for fantastic problems. One thing is clear that the complexity is growing dramatically. The complexity on the software side is growing, and the complexity on the infrastructure side is growing, right? It's a pressure from the software to be more efficient, right? So if you look about, this is what I look at the history, right? I'm trying to see the trends. When we started Spark, of course, we just focus on distributed computing. Every node was more or less the same, has a CPU and some memory and a disk drive at that time. Actually, when we went to disk drive from to solid disk drive, devices, SSDs, It was, we need to re-architect a little bit because, the serialization was no longer the bottleneck, was now the bottleneck. So that's one. But then when we started Ray, it was, okay, CPU and GPUs, NVIDIA.
Yeah.
But if you look today, what is you have there, you have you have every cloud trying to advance their own GPUs for strategic reasons as well for other reasons. And even if you look at NVIDIA, you have so many, type of GPUs. So you look at that diversity. And then you look not only that, you look at the networking, right? You have InfiniBand, RDMA, all of these things, right? And now you look about memory hierarchy, right? It used to be, RAM, CPU RAM, a bunch of caches, and just the persistent storage. Now, if you think about, you have for the GPUs, right? It's like you have HBM, and then you have the cache. Then you start to have this kind of very complicated hierarchies with and cache coherence between the HBM and the CPU memory, right? It's like Grace Hopper and MI300X, which is also sharing, DRAM, GRAM. So it's very, very complicated. So I think that it will be a lot of, innovation about how you are going to support this kind of extreme heterogeneity to make it easier for the developers to develop their application and take advantage of this hardware, right? I think that's one thing. And it will be at all levels, because another trend is that everyone is trying to do vertical integration to get better performance, lower cost, right? So compilers, frameworks, everything. The second point I'm going to make is that if you look about large language models, one of the biggest problems today in the industry is reliability.
Yeah.
Right? We see they can do fantastic things. Now, can they do, and if you talk with most of the enterprises, can they do them repeatedly? It's about reliability. So I think that's going to be a challenge for the next couple of years.
Well, I can tell you, Jan, as we started, no one has done a better job in this world of creating labs, creating open source communities that come out there, creating companies out of that. I know this audience can't wait to see what you do next. So thank you so much for being with us
Thank
today.
you for having me.
We really appreciate it.